In previous lessons, we talked about bandwidth challenges during network construction. Now, we are going to discuss how to cope with them. An equation called Shannon's theorem is worth mentioning in this discussion. C equals B times log 2, 1 plus S divided by N. In the equation, B, C, and S divided by N stand for carrier bandwidth, date, rate, and signal-to-noise ratio, or SNR, respectively. SNR, in other words, means signal quality. The equation proposes that increasing users' data rate requires increasing carrier bandwidth, or SNR. Given that SNR is affected by external environmental factors that may be beyond control, increasing bandwidth is often the only feasible option left to enhance the data rate. An analogy for how this works is a road. Bandwidth is like a road, while data can be seen as vehicles traveling on the road. The wider the bandwidth, the more data can travel on the road. Spectrum resources are indispensable for wireless communications and are another key factor affecting data rate over the air interfaces. For 5G in particular, there must be enough spectrum resources to guarantee ultra-high data rate. A problem has arisen, however, as 2G, 3G, and 4G networks already occupy the majority of sub-3 GHz spectrum resources, leaving little spectrum resources to accommodate continuous provision of large bandwidth. This means that 5G networks will have to make use of higher frequency spectrum resources, which are unoccupied. As shown in the diagram, electromagnetic waves can be categorized by frequency range. Signals transmitted over different frequency bands have diverging propagation characteristics. Live network communications mainly use intermediate and ultra-high frequency bands, leaving high and super high frequency bands available for 5G networks. The adopted 3GPP R15 specifications divide 5G spectrum into two frequency ranges, or FR. FR1 is a collection of low-frequency bands of less than 6 GHz, or sub-6 GHz, which are expected to serve as the primary bands for 5G networks. Frequency bands less than 3 GHz are known as sub-3 GHz bands, or C-band. FR2 is a collection of millimeter wave bands. These bands are high frequency and a large amount of them is available. FR2 is considered a supplementary spectrum for 5G networks. Considering spectrum resources are different, 3GPP specifications stipulate different maximum bandwidths for carriers within FR1 and FR2 categories, respectively. The diagram shows that the minimum carrier bandwidth in the sub-6 GHz bands is 5 MHz, and the maximum is 100 MHz. For millimeter wave bands, the carrier bandwidth ranges from 50 MHz to 400 MHz. The upcoming 3GPP R16 specifications will be likely to set the maximum carrier bandwidth to 800 MHz. The current 3GPP R15 specifications exclude the 1.4 MHz and 3 MHz bandwidths from being used for 5G, and reserve 4 current LTE bandwidths, 5 MHz, 10 MHz, 15 MHz, and 20 MHz for future 5G use, as networks evolve from LTE to 5G. Now, let's take a look at global allocation of 5G spectrum resources, including sub-6 GHz and millimeter wave bands, and how 5G networks deploy such bands. The diagram shows that China has assigned sub-6 GHz and millimeter wave bands for 5G use. Among sub-6 GHz bands, 5G bands span across 2.515 to 2.675 GHz, 3.3 to 3.6 GHz, and 4.8 to 5 GHz frequencies, with a total bandwidth of 660 MHz. Among millimeter wave bands, 5G networks can use 24.75 to 27.5 GHz and 37 to 42.5 GHz frequencies, with a total of 8.25 GHz available. Other countries have adopted similar spectrum allocation approaches. Generally, there are less C-band spectrum resources available compared with millimeter wave spectrum resources. However, as C-band provides as much as 200 MHz continuous bandwidth and its supply chain is maturing, with well-developed network and terminal devices, C-band will most likely become the universal working frequency bands for 5G. As the industry develops, other frequency bands will also be put into use. We've discussed the allocation of 5G spectrum, including how C-band and millimeter wave bands are allocated in China. We should also consider how sub-3 GHz resources can be reused for 5G as a result of spectrum reshuffling when 2G, 3G and 4G networks are gradually phased out. Sub-3 GHz bands, C-band and millimeter wave bands will be deployed for 5G networks in the future. But will 5G networks use these frequencies at the same time? No, at present. The higher the frequency band is, the poorer the coverage is, and vice versa. Generally, millimeter wave bands will be used for hotspots in areas such as railway stations and airports. C-band will be mainly used to provide wide coverage in urban areas, as it outperforms millimeter wave and sub-3 GHz bands in terms of network capacity and coverage. Sub-3 GHz bands offer optimal coverage thanks to their low-frequency transmission features. They are therefore also ideal deployment choices for wide coverage. Let's now explore some of the advantages and disadvantages of deploying sub-3 GHz bands, C-band and millimeter wave bands. Sub-3 GHz bands are currently occupied by 2G, 3G and 4G networks. As a result, sub-3 GHz band spectrum resources have to be vacated and reshuffled in order to be used for 5G deployment. C-band, in contrast, is newly added for 5G networks. C-band frequency bands have more resources available compared with sub-3 GHz bands and are capable of providing a continuous bandwidth of 200 MHz. They also have better coverage than millimeter wave bands. C-band scores high in capacity and coverage performance and will therefore play a key role in the early stages of 5G deployment. Millimeter wave bands have the most spectrum resources available. However, communication at such high frequencies is subject to high attenuation and signal absorption, meaning that millimeter wave bands are not suitable for wide coverage. Instead, they can be used in high traffic scenarios to transport large volumes of data. In this lesson, we explored 5G spectrum planning and deployment strategies. Spectrum resources with different features will be used differently. Sub-3 GHz bands and C-band will be used for wide coverage, while millimeter wave bands will work for additional capacity boost in hotspot areas. That's all for this class. In our next lesson, we will discuss new 5G technologies.